sorry about that. Because I think him up saying this meeting is being recorded, and I went to click on continue, but I accidentally clicked on leave meeting instead. Sorry.
Okay.
Yeah.
Good. Yeah, so I mean, for me, how I normally like to do these sessions, so I've done a good few at the moment now. So I think I've done 5. I've spoken to David Kaplan, who did the particle fever thing, and he spoke to me about dark energy, dark matter, and some universal energy stuff. I've spoken to somebody on cosmic microwave background
radiation. Great.
Radiation.
Good.
I've spoken to someone who works now at NASA about space exploration and more kind of practical observations of space. I have spoken to Sudan at CERN, and who's also working on the Dune experiment. So he's talking about neutrino detection and stuff.
Great. Yeah.
And what else have I covered? I think there was someone. Oh, and I've spoken to Don Lincoln. I don't know if you're familiar with him. I think he's been back and forth at CERN, but he kind of gave me an overview of a combination of experimental and theoretical discoveries that led up to our current understanding of the origins of the universe. And so obviously this project, as the title is the origins of the universe. Yeah. And what I hope to do is understand for this session what gravitational waves are, for example, because I haven't no background. And how does that link and the type of work you guys do at LIGO, how does that link to our current understanding of the origin of the universe? Yeah. So,
good. So I have a few thoughts as to how we might do this efficiently, ConScience. I've done a bunch of public lectures that have been recorded and are on YouTube over lockdown. I did one for India, I did one for Bangladesh last week. I've done one for the Institute of Physics in the UK. Nice. So in a way, well, delighted to talk to you, and I mean, you'll quickly learn I could talk till the cows come home about all this stuff. Yeah. I am conscious I don't want to kind of completely bombard you with stuff today. What might be useful is if I try and give you a kind of top level overview, and then recommend that you take a look at some of those talks I've given. They've been absolutely aimed at a general audience. They're not technical at all, Yeah, definitely. So, and you could just dip in and out of them. You don't need to watch them,
Oh no, I'll probably. I mean, how many have you done?
Well, I mean, I did a TEDx talk a few years ago that's only 15 minutes, and that was actually before we made the first detections. Okay. But nonetheless, still covers a lot of the fundamentals of what gravitational waves are and how we detect them. Okay. That was in 2014, and little did I know that, less than a year later, we would make the first discovery. Yeah. And then, obviously, since then, I do dozens of these a year, but they're different now because we've actually got detections to talk about. Of course, of course. And therefore the focus has broadened out a bit into telling that story of how we made the detection, not just about the hardware and everything, but about aspects of the people involved and working within a big collaboration of hundreds of people. That brings its own challenges. Of course, yeah. Of course. That's quite an interesting thing. So aspects of that would be great to chat to you about, but just so that you get a bit of context and all of that to begin with, then watching a few of these might be helpful.
Definitely. I will definitely look.
So I'll send you some links. So I'll drop you an email later today.
What was I going to say? Yeah. So just to I guess. Just to explain what are gravitational waves. Sure. Obviously, there was like the Nobel Prize thing, right, the other day and stuff. And so literally, I have no understanding, right? So
well, let's start off. Maybe if you don't mind, I'll ask you a question. What does gravity mean to you? What do you know about gravity from high school?
So obviously I did A-level physics, and we learned about Newtonian. The Newton's equation of motion, the laws of motion, I think. But
no, that's spot on.
Then actually since then, obviously through some of this research I've been doing now,
Yeah.
I've been, like, I spoke to David Kaplan about special relativity versus general relativity.
Okay, good.
And got to, because I didn't even know, but I had a suspicion about there was a link. But I think we discussed the link between energy and gravity, I think.
Mm-hmm.
But yeah, and then he started writing some equations, and I'm gonna go and sit down and look into that. So I'm up to like special general relativity.
Fantastic. That's a great place to start from.
Yeah.
I suspected that would be the case, but again, just didn't want to dive straight in. No, I mean, you'll see for yourself in my TEDx talk that I actually start off with Newtonian gravity, because, you know, that's kind of what people experience first. They learn about the whole story of the apple falling on his head and all that. Of course, yeah. And I mean, Newton's contribution was enormous. It was like totally groundbreaking to come up with a bit of maths that you learned about in your A-level that can essentially describe the gravitational force between apples and trees and, you know, the earth and the moon and all that. Yeah. And then we still, most of the time, at least in everyday life and even many aspects of physics research, just use Newtonian gravity. It's fine for most situations. It starts to kind of show its limitations when you're dealing with, you know, the kind of speeds and masses associated with CERN. Yeah. But in most practical situations, Newtonian gravity is fine. But the thing that really bugged Einstein about it, that maybe David talked about, was a more deeper kind of philosophical problem with Newtonian gravity. And it was, if Newtonian gravity says that gravity is a force, let's say between the Earth and the Moon, how does the force actually get from the Earth to the Moon? You know, it's just empty space.
Yeah, of course.
What does it mean to say that you've got a force acting at a distance from a massive body like the Earth to another one like the Moon?
Yeah.
So Einstein was deeply troubled by this. And he was also deeply troubled by the fact that, as you know from your discussions about special relativity, that according to special relativity, the magnitude of that force should look different to different observers depending on how they're moving.
Yeah, yeah.
And that didn't seem to sit well with Einstein. He didn't like the idea that, you know, something as fundamental as gravity would depend on your frame of reference, would depend on your point of view. So he basically took the whole thing apart and started again and came up with this idea of gravity not as a force at all, but as a bending, a curving of space and time. So he already had the idea of the unified space-time from special relativity, but that was just for people moving at a constant velocity. And what he then made the big leap to was to extend it to people moving at different speeds, at accelerating or decelerating.
Yeah.
And along the way, he brought in this really deep idea that actually gravity and acceleration are equivalent to each other. That they, you know, just like if you're driving in a fast car, you feel yourself being pushed back into your seat. Yeah. Well, that's because the acceleration makes you feel heavier. You know, it's a similar sensation to feeling the weight of the Earth's gravity. Yeah. So Einstein just ran with that idea that gravity and acceleration are not just similar, they're actually the same. They're the same thing. And you can't tell the difference between being accelerated and being in a gravitational field. And all of that led to general relativity. It led to, over 10 years, him realizing some quite dramatic consequences of that, like the bending of light in a gravitational field, what we call gravitational lensing. Yeah. And another one of the predictions of general relativity was gravitational waves. So gravitational waves are ripples in space and time caused by changes in the curvature of the gravitational field. So we have often a kind of metaphor, people think of like a big stretch sheet of rubber, like a trampoline, and you drop a heavy object in that and the trampoline bends.
Yeah.
Well, that's fine. It's not a perfect analogy, but it's actually pretty good for thinking about, say, the Earth sitting there and generating a gravitational field and causing, you know, the moon to orbit the Earth. It's like rolling a ball around the stretched sheet of rubber.
Yeah.
But where gravitational waves come in is when you kind of disturb the trampoline, when you shake it. You know, what would happen if you bounce up and down on the trampoline is that the rubber sheet will ripple, you know, where you hit the trampoline and it bends. That will cause the whole sheet to distort. It will sort of spread out from you. And that's what we are thinking of. Again, it's just a kind of simplified analogy, but it's thinking of space-time itself wobbling like that trampoline.
Okay. So is it modeling space-time as the gravitational field that does that motion, or is it?
Yes. Okay. So the gravitational field causes changes in that space-time curvature.
Yeah.
If the gravitational field is not changing, if it's just like the planet or star or whatever is just sitting there, then there won't be any gravitational waves. There'll still be curvature, but it's only when the curvature changes that you get those ripples spreading out.
Okay.
And then that begs the question, well, what kind of thing would make the curvature of space-time change? Well, in principle, me shaking my fist is doing it because I'm accelerating a massive body. But, it's not that massive, and I'm not moving it very fast. So consequently, the gravitational waves that generates are absolutely tiny. I mean, even the ones that we detect are tiny, but these are just unimaginably tiny. There's no way we could ever measure the gravitational waves produced by someone shaking their fist. So what we need to do is to use the universe as our laboratory and look for things that shake space-time way more than we possibly could with human scale and disturbances.
Yeah.
And the kind of things that do it are colliding stars, exploding stars, possibly even the Big Bang itself. So we were able to predict long before we made the first detection that according to Einstein's theory, if you had two compact stars like black holes, and they got close enough to each other and they were orbiting around each other, then that would be changing the gravitational field so much that it ought to send out into the universe ripples that we might just have a chance of being able to measure.
I see.
And that's what inspired generations of scientists to try and develop the technology to detect those ripples.